Good morning, everyone. My name is Sudheendra Murthy. I've been with eBay for the last 9+ years, primarily with the Cloud Platforms Group at eBay. So today we are going to be talking about how eBay is building a massive multi-tenant service mesh using Istio. So let's get right into it. Okay, so the agenda of the talk is going to be as follows. So we'll start off with introduction, give you an idea of the scale that we are talking about to run eBay applications and how applications are deployed within the eBay's cloud. And we'll then jump into our service mesh journey. And we also will look at reasons for us to be doing service mesh. And next we look at some of the scale testing results that we did to validate Istio scale to run eBay's applications. And finally, we look at some of the things that are ongoing, some of the open questions, open problems that we are looking at as part of the future direction. Okay, so eBay marketplaces at a glance. So at any given point of time, eBay has around 185 million active buyers worldwide. And there are about 19 million sellers worldwide. And at any given point of time, we have an average of around 1.7 billion live listings of items. And the last quarter, we had about $26 billion of GMV come in Q4 of 2020. So how does to support this massive scale, how are the applications laid out? So the eBay is essentially powered by more than 5,000 microservices. So we use leverage microservice architecture, and we have all types of microservices, ranging from like search engines, API services, databases. We have big data systems, machine learning, logging, tracing, and different messaging systems. So we use a lot of open source technologies and projects internally. And also the microservices are written in a variety of programming languages. So we use Java, Python, Golang, Scala, to name a few. There are even microservices being written in Rust and some of the other languages that are coming up. And also these microservices, they run on a variety of hardware. So we have the general purpose x86 machines. We have GPUs for all the machine learning tasks and things like that. So now, how are all these applications deployed in our cloud? So eBay has internal cloud in multiple data centers. The layout of our cloud is roughly as shown in the picture. So we have multiple data centers across different geolocations, or what we call them as regions. And in each data center, we have a number of availability zones, or AZs for short. So each AZ has completely independent power cooling networking. So it forms a separate fault domain. And besides the data centers in a number of regions, we also have a number of points of presence, or POP locations, across the globe, where we peer with the internet service providers and to be closer to the customers. So from an architectural point of view, we treat the POPs as mini availability zones. Now, how our Kubernetes, we have a number of Kubernetes clusters that are deployed across these availability zones. So we map the Kubernetes clusters to be within an availability zone. So the idea is it follows the shared nothing architecture, and the Kubernetes cluster doesn't span across multiple AZs, the clusters that are hosting the microservices. So each Kubernetes cluster has anywhere from 200 to 5,000 servers or nodes, and there could be up to 100,000 pods in a cluster, hosting about 10,000 plus Kubernetes services. So these services include all different the different life cycle stages of our microservices, like production, pre-production, staging, etc. And these applications are essentially deployed for high availability across multiple regions. And even within a region, we try to deploy these applications in multiple AZs. The idea is, or the goal is, to have the capability to run all the applications or entire eBay site from a single region or an availability zone in a worst case scenario. So in a worst case scenario, even if n-1 regions fail, we want to be able to run the entire site from the nth, the last region. So that's our aspiration. And with so many availability zones and data centers, so how do our developers deploy their applications? So to help our developers, we have a hierarchy of control planes. So each control plane is a Kubernetes cluster. So we can think of them as Kubernetes clusters, but they are hosting services that are responsible for delegating controls or services that serve things at that particular level in the hierarchy. So for example, we have this global control plane. So global control plane is where users submit their application specs. So these could be deployment specs, and as we will get into a little bit later, these could be what we call as access point specs to represents the load balancing, traffic management specs. And the function of the global control plane is to take the specs and delegate it to the AZ control planes. And the AZ control planes, when they get the specs, their responsibility is to spread it and delegate it to or sync it to the Kubernetes workload clusters in that AZ. And as I was mentioning a little while ago, so we use this shared nothing model. So where even the AZ control plane is responsible for orchestrating things within the AZ. So if there are component failures in the AZ control plane, that affects only that particular availability zone, and it doesn't impact the other availability zones. And in addition to delegating the specs, these control planes also host services that are specific to the availability zone, or even the services that need to be available globally. For example, IPAM, or IP address management, is one such service where it's deployed in every availability zone, and it takes care of giving out IP addresses for all the workloads, all the pods in that AZ. So so with all these workloads deployed in these clusters, so how does the load balancing and traffic flow work? So this gives a pictorial view of the traffic flow. So we have 2 tiers of hardware load balancers today. So the web tier and application tier, or app tier. So the app tier load balancers are where the Kubernetes services are realized. And the backend of the app tier load balancers are the individual, the application pods. And the web tier, primarily all the app tier load balancers become the members of the web tier load balancers. So the web tier load balancers is where we control what percentage of traffic has to be sent to which particular availability zone. And in case of, if we want to take out an application from a particular availability zone or particular region, so we have controls for those in the web tier load balancer. So for example, the arrows here show the connectivity or the data, the traffic flow. So if, for example, we want to take out all the traffic for a particular application from AZ1, so the controls here will make sure that the percentage of traffic going here is becomes 0, and it's spread across the other two availability zones, as an example. And the client, through DNS, it connects to the closest web tier load balancer. So what about the security? So we have L4 microsegmentation solution, which essentially has a central policy store that's capturing primarily dependencies from application to application. And we have a set of controllers that watch on all the Kubernetes clusters, and they translate these application to application dependency into Kubernetes network policies, and they push the network policies. So we can think of these, the policy store and this layer, as one layer on top of the Kubernetes network policies. And given the variety of workloads, and given our previous deployments in legacy, OpenStack, and bare metals, we also take the same policy store, and we also have enforcers to enforce them on hardware firewall devices, bare metals like OpenStack, and so on. And we also have TLS for transport security. And today these are implemented in a variety of ways. In some cases, the applications implement TLS. And in some cases, we do have a statically configured Envoy, which is co-located with the application that takes care of handling TLS and all the aspects about certificate rotation and things like that. In addition to the layer 4 microsegmentation and the TLS, we also have a custom OpenID based implementation for layer 7 authentication, or what is called as the origin or request authentication. So this is the current lay of the land. So now, what are the main challenges with this picture? So the current challenges include the intractability of managing the hardware devices, like the load balancers and the firewalls. Essentially, the managing hardware devices, from our experience, we have found it to be quite challenging, and it's slow, and also there are reliability concerns. So this is one of the reasons why we are looking at service mesh, and how to get rid of the hardware devices and move things to software. That also gives us more improves our agility and the speed of the rollout and things like that. And in addition to that, the layer 4 segmentation that we have, achieving that microsegmentation at full scale of eBay is quite challenging, because the solution relies on IP addresses, and if IP addresses are constantly churning, if pods are going down and things like that, then it's hard for this microsegmentation solution to keep up with the changing IPs. So even with network policy, where the policy is enforced on using label selectors and all, that is still confined to a single Kubernetes cluster. But since workloads are spread across multiple regions, we still need to accommodate for IPs changing in other clusters and then reflect it onto every cluster. So doing that at scale is quite challenging from our experience. And another aspect of it is enabling TLS for all applications in a consistent way is also one of our requirements. Without this, so there are a lot of touch points with the application teams, and we have to work with them. So one of the things we are looking for is, how do we get end-to-end TLS for all the applications in a consistent way, without making too many changes within the application itself. And these are some of the primary reasons for which we are looking at service mesh. And how do we see service mesh? So service mesh for us, we see it as an architectural pattern that implements the security, observability, service routing, and discovery functions as features of the infrastructure. So we're taking these used to be features of the applications done in different variety of ways within the applications. So we are taking that into the infrastructure. So that's how we see how we see the power of service mesh playing out. And some of these functions include TLS termination, traffic management, tracing, rate limiting, etc. So these are, how do we look at the service mesh journey? Like, our service mesh journey can be thought of as 4 distinct stages. So the first stage is where we looked at the entire access, the traffic management, and all these specifications. So these specifications existed in load balancer devices or different systems. So our first idea was to get all the aspects of traffic routing and traffic management of an application into a standard set of specifications. So now, once we have this specifications, we use the same specifications to program the hardware devices, hardware load balancers. So that was our first step. And the second step, and as part of the first step, we also changed all the internal tools that interacted with these devices directly to go through the standard set of specifications. So this becomes like a single funnel or single entry point for changing all aspects, traffic aspects of an application. Then our next step, with this in place, our next step was to replace the hardware load balancers with the software counterpart. And the idea is, when we do the step 2, since in step 1 we have unified all the specs, so the step 2, when we swap out the hardware with the software, it's transparent to the end users. So from their point of view, it is the same set of specs, but behind the scenes, instead of applying it on a hardware device, it's getting applied on a software device. And this is the step 2 is where we are currently placed, and we are in the middle of doing this. And the next steps, parallelly, we are working on the next 2 steps are, how do we, with step 2, we had the simple deployment of Istio, where we mapped Istio to individual Kubernetes clusters. Now, step 3 is where we are looking at evolving that architecture into an availability zone architecture, like moving Istio to an availability zone. We will get into the details in a little bit. And the next step is to evolve security. So these 2, I think, we'll go in a bit more detail. So talking about the unified specs to capture the traffic management and intent, one of the things we did is to leverage Istio objects. So what we essentially did is, we took all of the Istio, the different objects of Istio, like gateway, virtual service, destination rules, service entries, and workload entries, and we essentially embedded them into this higher level access point specification. And some of the main things to notice here are, the access point spec has what are called as scope IDs. So scope IDs determine which particular availability zone or a cluster should this specification be realized in. And we have a set of controllers, so that essentially take this spec, and they, using our hierarchical control planes, so they move the spec down from global control plane to the individual Kubernetes clusters or individual Istio control planes. And as part of this, we also, as I mentioned, we also started changing all our other internal tools, like monitoring tools, UI tools, and things like that, to start using these unified specs. So instead of interacting with load balancers or interacting with these devices directly. And our step 2 was to then switch the hardware load balancers with the software stack. So this is our software load balancer stack, how it looks like. So this is so we have two main components. We have a network load balancer, or this is a layer 4 load balancer, and the Istio ingress gateway. So the network load balancer serves two primary purposes. So one is this takes care of advertising the WIPs to the outside world, to the clients using BGP to attract traffic for that WIP. And then the other function is it tunnels and sends the traffic in a consistent hashing way to the backend ingress gateways. So the consistent hashing ensures that the same 4 tuple or 5 tuple gets mapped to the same gateway, same backend instance of the same gateway. And also the consistent hashing. So we have an implementation based on maglev. So that ensures that the load is near uniformly spread across the backends. And also if any of the backend gateways should go down, so the load distribution also is actually done in a near uniform way. And if you look at the request traffic, so from the client, the request traffic hits the network load balancer, and then it's sent to the ingress gateway through the tunnel, IP in IP tunnel, and to the pods. The return traffic, however, since this path is tunneled, the return traffic goes directly back to the client from the ingress gateway in a DSR fashion. So the another point is, today our network load balancers are based on IPVS in kernel. So we are also working on a more efficient eBPF and XTP based implementation. And the Istio itself, for simplicity, at this step, so for simplicity, we deployed it as one Istio deployment per cluster, per Kubernetes cluster, as simplicity. But there are some challenges with this deployment. One challenge is, though this deployment is simple, the traffic between the two clusters within the same AZ, they go through the Istio ingress gateway, so they become north-south traffic. So we would like to have pod-to-pod traffic go directly as much as possible. So we move to we are moving towards the AZ-based deployment, where we are following the primary remote setup of Istio, where the one cluster, Istio in one cluster, acts as the primary. It watches API servers on other clusters. And the next step for us that we are looking at is to evolve security. So we are looking at mutual TLS as a way to enforce dial tone security, or what's called as peer authentication. So for this we are leveraging the SPIFFE trust domain. And in SPIFFE trust domain, each workload gets a unique identity. And in order to ensure that every workload has a unique identity, so we also have a few assertions that we are ensuring across the fleet. So one such assertion is, each namespace, we are making sure it's globally unique. So, and then each deployment that goes into these namespaces are associated with a unique service account. And what we are essentially looking at is, taking this trust domain and mapping it to the different workload environments, such as production will be one trust domain, pre-production workloads are going to be another one, and PCI, and so on. And we have this requirement of, since we run these multiple workloads in each Kubernetes cluster, we had to support multiple trust domains within a single cluster. But today there is a limitation in Istio, where one Istio deployment supports only one trust domain. So what we essentially did is we have multiple deployments of Istio within each Kubernetes cluster. And each of these Istio deployments is watching on a subset of namespaces in that Kubernetes cluster. So we had a custom implementation. Now there was a recent discovery selector pull feature that got merged into Istio. So we are starting to leverage the upstream feature. So overall, the idea is we use the trust domains and mutual TLS to create these macro segments for individual environments. And I have a few more slides. So for origin authentication, we have an internal implementation that we are planning to extend with Istio. And the other question, this is coming to the last part of the talk. So the one question we had was, how does it all scale to the eBay application scale? So we did extensive data plane and control plane testing. So data plane of Envoy is well documented, but control plane scale testing is where we didn't find good documentation upstream. So our primary goals was to mainly understand the proxy convergence time, which is when we have these thousands of proxies and a lot of state, how soon the proxy convergence happens. And let me jump into the results. So one of the things we noticed was since we initially had wide open egress sidecar configuration, so this was essentially pushing the state of the entire cluster, all the services endpoints, to every sidecar proxy. So this doesn't scale, even though the particular application doesn't talk to all other services. We are still pushing the complete state. So for the testing, we disabled the egress traffic, and after that, we were able to proceed with the scale test. So the main takeaways were our 99.9 percentile convergence time for up to 3,000 sidecars was under a second. And also we noticed pilot can scale horizontally. So what it means is every 3,000 sidecars we can 2,000 to 3,000 sidecars we can have one instance of pilot or STOD. And some of the future things we are looking at are we are looking for the support for on-demand config pushes. As I mentioned, we need the sidecars to get only the configuration that it requires. And also we are also looking at how do we extend Istio to support multiple trust domains within the same Istio deployment. And some of the other open problems we are looking at is the gateways between two different availability zones. How do we bridge them so that it's MTLS with mutual TLS with trust flowing all the way from one pod to another pod in two different regions or two different availability zones. And the last bit we are looking at is how do we even scale the authorization policies. So we are looking at a scale of millions of policies, and there are issues about how do we federate the identity and so on. So these are some of the open problems that we are looking at. And this was a lot of content to cover within a 25-minute span. I went a little bit overboard, but if you have any questions, please feel free to reach us on Slack or at this DL, this email. So thank you for listening to the presentation.